Hey everyone, in this problem, you are given a one-index array of nums and number of integers, and a set of numbers is complete if the product of every pair is a perfect square. The perfect square means something that can be expressed of the product of an integer by itself. For example, 3 square 9, and 9 is a perfect square, and basically 3 integer square is a perfect square. And we need to find a subset of indexes in 1 to n, and the element sum is the value of that index. So that's why we need to do one index, because otherwise the product of 0 will be nothing. So that's why we need to at least have one index. And then we want to return the maximum element sum of a complete set of any chosen set in 1 all the way to n. Let's take a look at the example to illustrate the idea more. So in this example, you are given this array and the answer is 16. Let's see why. So apart from the subset consisting of a single index, that means because 1 square is 1 and 2 square is 4, so every index pairing with itself by definition will be a perfect square. So we're gonna ignore all this. So in the worst case scenario, you can see it will be the maximum of the nums. But apart from choosing just one element in the subset, there is another possibility we can choose more than one. For example, this 1, 4 is a valid subset because 1 times 4 is 4, which is 2 square, and also 2 times 8 is 16, which is 4 square. So for 1, 4, remember we are doing a one index, so 1 is here and 4 is here. 8 plus 5 is 13, and another possible subset is 2, 8, so 2 is here, and then 8 is here, so 7 plus 9 is 16, and 16 is larger than 13. It actually happens to be the largest, and that's why we return 16. So that's pretty much all for the example, and let's think about how can we solve this problem. So before we move to the solution, and I want to prove something first, which is going to be very helpful to us in crafting our solution. So the statement is something like this: assume x less than y and less than z. Basically, it is a distinct of 3 numbers where x is the smallest. And if x times y is a perfect square, so this 2 times is a perfect square, and y times z is also a perfect square, so assume this 2, then x times z is always a perfect square. So I need to prove this. Basically, if this is a perfect square and this is a perfect square, then I don't need to check this one and this one. So, but is that always the case? So let's think about this a little bit more. So if we say x times y is a perfect square, so it means that it will be some I times I for some integer I. And then we also assume y times z is also a perfect square. So it will be something like y times z is, let's say, j times j for some j, where j is an integer. And then we want to show that this x times z is always a perfect square. So this x times z will be a perfect square. So how can we show this? So basically, x times z is x times y, and then times y times z. Basically, I'm trying to plug this into the formula, but if we directly plug this, and you notice y appeared twice, so that's why we have to divide it back in here. And then we know that x times y is a perfect square because it is assumed it. So I times I, and then this will, y times z will be j times j, and then it will be something like this. And then if we rearrange the order, and we will get something like I times I, j actually, times 1 over y, and then times I times j times 1 over y. So you can see this is exactly the same as this. So basically, this integer will be the square, and x times z is a perfect square because it is, as we can think of this in this way. And I times j will be divisible to y because of this assumption here. So that's pretty much all. Once we have this statement, then we can move on to the next part of our solution. Now we have already convinced ourselves that this is true. How is that going to help us finding the solution? So if you take a look at any complete subset, it will look something like 1, 4, 9, and then maybe 16, or just maybe many more numbers. So if this is true, then because we want to maximize the element sum, and the element sum or each element will always be positive. So what I'm trying to say is that it's always better to start at the smallest index instead of starting at somewhere like 4, because if I start at something like 4, then it will have a subset like this, but it will always be possible for 1 to join in. So that's why we always start from the smallest. So with that information, we can just try to write the pseudocode to solve the problem. So something like for I in 1 all the way to n, and for j in I all the way to n with a step equals I, because we are trying to find perfect square that is divisible to I squared. So it doesn't make sense to add 1. So our step will always be I, and then we're starting from I. And if I times j is the perfect square, then current plus equal to array of j minus 1, because we have to do minus 1. The given number will be 0 index. This j and this I is 1 index. So that's just a minor thing that we have to do. And then we just compare all the maximum curve and then return our answer. That's pretty much all for the solution overview. And let's see how can we actually code this up. So first, I'm going to initialize a point variable, and it's the length of the nums, and then answer initialize 0, and square is a set that later I'm going to fill it for checking if it is a perfect square for some number quickly. So for I from 1 to n inclusively, and then we're going to add I times I to the square. So later we can use that square set to check if the certain number is square or not. And then we also need this mock array. As I mentioned previously, if the subset is complete, it means every paired product is a perfect square. We want to start from the lowest, because this will give us the largest size of subset possible. Then we're gonna go from I to n plus 1 again. So if it is already mocked, it means that there is already a smaller element in that subset that can match with me, then I'm just gonna not bother looking. Otherwise, if it is first time C, and then initialize current value as the nums I minus 1, because this nums is 0 index, and then we're gonna look for every possible perfect square that is divisible to I squared, which is I times I. So we start from I itself. So this is possible because I times I is a perfect square by definition. And the next step we're gonna check is not I plus 1, but I plus I, because we are trying to look for perfect square that is divisible to I times I. So it doesn't make sense to do I plus 1. In fact, step will always be I. So if this I times j is a perfect square, then we're going to mark j as true. So later we don't want to visit it. And then our current answer will plus equal to nums j minus 1, because we can include index j into our subset. And after that's done, we're going to take the maximum of all current and store that in answer, and eventually just return answer. And the time is n log n. Although it seems like it is the next for loop here, but you can see the step of each j actually increased. It's actually called a harmonic series in computer science. So it's actually a famous concept, and try to make GPT-4 to explain the time complexity of it, and I think it's a pretty good job. And I'll share the link to this bonds as well, so you can check. And for the space complexity is ON. It's quite obvious. It's because it's coming from this square set, and it's also this mark array. Both of them will be size n. Okay, that's pretty much all for it. Let's try to submit. Okay, accepted. Thank you so much for watching, and I will see you next time. Bye bye.